I want to talk about a joint work with Yongquan Hu. So I'll give the first of the two talks, and I think he will continue with the second talk. So here, this is a plan of the talks. First, I'll recall some background, which has already appeared in the lecture series of Stefano Mora and Ibrahim Shahan. And then I will mention some known results you have already seen many times. And then I'll talk about the first couple of our main results, and I'll sketch a proof of these results. And Yongquan will talk about the rest of the results. So let P be a prime number, and take a totally real extension of Q in which P is unramified. And D is a quaternion algebra, so here I assume it's indefinite for the presentation. You take F is a sufficient large finite extension of Fp for our coefficient field of all the representations. You take R bar is a global Galois representation, which is from the absolute Galois group of F to GO2F, which is continuous, absolute, irreducible, and totally odd, and we will assume it's modular. Take K, so that K be a open compact subgroup of the finite ideals of this quaternion algebra, and XK will be the Shimura curve of level K. So it's a smooth projective curve over F.
Sorry.
So this H1 will be the tau cohomology of mod P coefficient of the Shimura curve. So here I will write pi d R bar will be the R bar isotypic part of this tau cohomology, and you take all this level. You take all this K as finite, this open compact subgroup of this finite ideals of the quaternion algebra. For the convention here, I just I should twist it by the second character. So I take twist, and we know that we assume this is non-zero, and it's of course it's a smooth representation of this eidetic group. So this is a conjecture made by Mazur Diamond Jarvis. So the conjecture that this pi dr bar should have a restrict tensor product decomposition, where W is over all the finite places of this F. Okay. But we don't know if this conjecture is true now at the moment. So the goal here is to we will fix a P. Oh, sorry, we will fix a place a V above P in all this talk, and we want to understand this local this is a local part at this is pi V D of R bar. Although this decomposition is conjecture, but Bordeaux diamond they have so we expect this local component should only depend on the restriction of the Galois representation to the decomposition subgroup, and it shouldn't depend on the choice of the real field or the quaternion algebra or the there should be R bar here. Although we don't know if this conjecture is true, but Bordeaux diamond and Emerton G sub, they constructed such a local factor of this pi d R bar, and if there is such a decomposition, then the representation they constructed is a local factor at V. But their construction depends on following assumptions. They assume the following assumptions on R bar. Maybe here I assume like more restrictive assumptions because I will need all these assumptions for our main results. But maybe they don't need to assume p is bigger or equal to 7, maybe bigger or equal to 5 or something like that. But for us, we assume that p is bigger or equal to 7, and the restriction. So the R bar is to the Galois group of the F joint the this p root of unity is absolutely irreducible, and some other assumptions. So so at p we only assume all this weak genericity condition for their construction of this pi vd R bar. So let me recall Gelfand-Kirillov dimension before we recall all these known results. This already appeared in the lecture of Benjamin. So so V here is the fixed place over P. So I write F for the degree of the extension, Fv over Qp. And I write K for the GO2O Fv, and Ky is the kernel from GO2 V to this mod P. So this definition of Gelfand-Kirillov dimension is that for every pi smooth admissible representation of GO2O Fv over this finite field, there is a unique integer which we're going to call this GK dimension of pi, which is between the 0 and the dimension of K1 as a p-adic group, such that you have you can find two real numbers satisfy this bound. So this dimension of this pi of the fixed points given by the K1 to the p to the nth, this congruent subgroup fixed points of pi over this p to the n times. So this is a unique integer gk of pi satisfy this property. So I think this is an equivalent definition given in the probably second lecture of Benjamin. So there are some examples. If f is 1, we know the GK dimension of principal theories is the same as the GK dimension of supersingular representations. They're all 1. So the results. This is the results of Pascunas and Stefan Mora. For general F, as Benjamin explained in his lectures, that it's easy to compute the principal theories. So the GK dimension of all principal theories, universal principal theories, are just F. So now here's some known results. So because we're only interested in the local factor pi vd of R bar, and I mean conjecture is this local factor only depends on the restriction of the R bar to this local decomposition group. So by abuse of notation, we just write this rho bar to be this local this restriction of R bar to the local decomposition group, and we're gonna write this pi rho bar for this local factor. So we although probably it depends on the choice of D, but we don't know. But let's do this, and we fix the central character of pi rho bar. So when f is 1, I mean so when this when the degree of this local. So when this f, this total real field extension is Q and D is GO2, then Benjamin explains that this pi rho bar explicitly null. And in fact, we know that this GK dimension of this pi rho bar is 1. And this pi rho bar depends only on rho bar. Okay. And this pi rho bar is of finite length. Okay, and this is the results of Bordeaux, Coleman, Emerton, Kieson, Pascunas, and probably many others. So this is the case where, well, we believe that if this the field extension of FV over QP is 1, so is FV, if FV is this local, if FV is QP, then we always believe that this property should hold. Although probably it's only written for the case where this number field is Q and D is due to. So now we assume that probably we're gonna treat a case where this degree is probably bigger than 1. So let me emphasize that we're only in the unramified case, because at the beginning I assume that my prime number P is unramified in this total real field F. So W rho bar is a set of Serre weights introduced by Professor Diamond. Here's the weight part of the Serre's conjecture. So that's a result of G. Gieson and G. Leo Savit and Emerton G. Savit. So theorem is that the pi rho bar so the K circle of this pi rho bar. So K is just GO2O FV. Depends only on rho bar. Okay, so in fact we can write down its circle. So it's just a direct sum. Well, circle is the maximum semi-simple subpermutation. So it's direct sum of sigma, where sigma runs over all the set of Serre weights. So let me introduce more notations. So so I want to write I for this Iwahori subgroup. And this I1 is P Iwahori. And Z is the center of my group G here. And Z1 is Z intersect with K1. We know that Z1 acts trivially on pi rho bar. So here's the maximum ideal of the Iwasawa algebra of I1 over Z1 will be denoted by M I1. I think that's Bordeaux used MI for this. Yeah. So the Emerton G. Savit, they show the following theorem, that this pi rho bar I1 invariant, which is also the M I1 torsion points of this pi rho bar is explicit now, and this finite dimensional vector space only depends on rho bar. Okay, and not just the finite dimensional vector space. It's just I over I1 representation. It's a representation of the torus. So this is for I1 invariant. Then we can go further. So namely, we want to consider the K1 invariant. So this is the representation D naught rho bar introduced by Benjamin yesterday. So write gamma for this K over K mod K1, which is isomorphic to GO to F of P to the F. So the Bordeaux-Pascunas, they show that there is a unique finite dimensional representation D naught rho bar of gamma over F, such that the circle is the right one, is a right circle, and each element, each Serre weight, only occurs in the circle of this D naught rho bar. And this D naught rho bar is a maxima for this property 1, 2. So it's a maxima. So the largest subrepresentation of the injective envelope of the of all this the injective envelope of all the Serre weights, such that the Serre weights only appears in the circle, and this D naught rho bar is explicit and is multiplicity free. They show this properties of this D naught rho bar. Okay, so here's an example of this D naught rho bar when rho bar is reducible non-split. So you can write a rho bar restricted to the inertia is of this form, so cyclotomic to the R plus 1 and 1, and here because we assume it's non-split, so star extension here is non-trivial. So this D rho bar is of this form. Okay, so the first sim R F square is a Serre, is a set of Serre. So this one is a W rho bar. So this is a circle, and the model circle is a direct sum of two weights, two irreducible representation of gamma. So this is a D naught rho bar, and if we write this maximum idea of Iwasawa algebra of Fk1 over Z1 by frac M Mk1 is the maximum ideal, then we have the following theorem. So it's proved in by Yongchuan and myself, and Mora Shahan in the semi-simple case, and it's finished by Lei for all cases. So the K1 invariant of this pi rho bar should only depends only on rho bar. So, and in fact, this K1 invariant is a D naught rho bar defined by Buhay and Pascunas. So in particular, this because we know this D naught rho bar is multiplicity free, we know this pi rho bar K1 invariant is also multiplicity free. Okay. So now let me explain our main results. So I make some assumptions on this rho bar. So this IFV is inertial subgroup, and this omega F is a Serre's fundamental character of level F. So I only so in this for our main results, we should assume that the rho bar is reducible, and rho bar is strongly generic. So that's more restrictive genericity assumption than usual. Okay, so then the weak generic assumption. So we assume that R bar is between 2 and p minus 5. So in particular, p should be bigger or equal to 7. So from now on, we assume that rho bar is reducible and non-split. So the star is non-zero, and also rho bar is strongly generic in this sense. So we with Yongchuan, we give a definite extension of the a generalization of D naught rho bar given by Bordeaux and Pascunas. So we denote it by D tilde not D naught tilde rho bar. So instead, so here we write this gamma tilde for the. So remember, gamma is just F double bracket K modular Mk1. So for gamma tilde, we denote we use to denote the F of a double bracket K modular Mk1 square. So this is square here. This is larger than gamma, so we should look at larger representations. And so we show that there is a unique finite dimensional representation denoted by D naught tilde rho bar of gamma tilde. over F, such that the circle, the gamma tilde circle of this representation is the same as the gamma circles. It's just a bunch of Serre weights, so you have sum of the Serre weights, and each Serre weight only occurs in the circle, and we so we take d naught 0 d naught tilde rho bar, which is maxima for these two properties. So the circle is the right circle, and the every Serre weight in the circle only appears in the circle. So you take the maxima 1, and we can show that this d naught tilde rho bar is multiplicity free. So here's some remarks over rho bar. So I already assume that rho bar is a reducible non-split. Okay. So when rho bar is a reducible split and rho bar is irreducible, so in the semi-simple case, this result is also obtained by Bordeaux, Hersig, Mora, Shahan in spring this year. So here's an example of d tilde rho bar when f is 1. So I assume that my rho bar is reducible non-split. So this is the d tilde rho bar. So the first two terms here, so it's a length for 1, 2, 3. Yeah, so you have 4. This is length 4 filtration. So the circle filtration, and this is a Serre weight for rho bar, and the first two here is a d naught rho bar, but you have like 2 more pieces. Okay. So it's larger representation. So here's our main results. So maintain all these assumptions we have made on R bar and rho bar. So namely, R bar should at least satisfy all these Taylor-Wells assumptions, and this rho bar is strongly generic and reducible non-split, and yes, and strongly generic. And further, we assume that this condition, so namely, we want to make the local deformation ring at places over P, but yeah, we make this local deformation ring formally smooth. So the theorem is that first is a GK dimension of the pi rho bar is F, so it's as expected, and the second part is if you look at the pi this mk1 squared torsion part of this pi rho bar, then that's just the d naught tilde rho bar. As d naught tilde rho bar is multiplicity free, we know this killed by this maximum this m square is also the pi rho bar killed by this m square is also multiplicity free. So let me make some remark before we sketch the proof of these two. So the first in this big paper, this Bordeaux, Hersig, Mora, and Shahan, they proved the similar results for rho bar semi-simple. And even they proved this for non-minima case, meaning that you remember that in the lectures of Benjamin, you have this multiplicity, some space to the R. So so for our results, we only consider the minima case, but they can do this for non-minima case. And the second remark is that we already know that G Newton proved this lower bound for this GK dimension. Okay, so for this, so they prove this the GK dimension of pi is at least f. So therefore, to prove this equality, we have to show this upper bound for this GK dimension. And for this part, we should apply the control theorem, which you will see later. This control theorem proved by this BHHMS. So to compare the methods in this BHHMS, they need to compute the crystalline deformation ring of Robov Hochschild with 2 minus 1. So this is a really heavy computation, and for our results, we because we only consider this reducible non-split case, so we only need the results of the Daniel Lay on the crystalline potential crystalline deformation of Hochschild with 1, 0. So let me sketch the proof. Okay. And so let's do the first reduction. So the first, so let me say that we are reduced to show that for any sigma in the Serre weight, the Serre weight of Robot, sigma only occurs once in this pi Robot MK1 square. So this theorem A is equivalent to theorem B, okay, because you only, so here for sigma in the Serre weight, this projective, this push gamma tilde sigma is the projective envelope of sigma in the category of gamma tilde modulars. So this is this A is equivalent to B. Okay, so you take the home from the projective envelope to this pi Robot, and you look at the dimension over F, it's just 1. Okay. So let's assume theorem A, and then I'll tell you why this theorem A with the results of with the contour theorem of BHHMS gives 1 and 2. Okay, so let's assume theorem A first, and then I will tell you how to prove theorem A. So let's assume theorem A. So why is theorem A implies 2? So well, I mean, it's just a definition. Because this D not tilde Robot is the largest representation of property 1, 2, and because if you know theorem A, you know that the Serre weight only appears once in the circle. So you have this inclusion, okay? And the projective property of M infinity. So M infinity is a patched modular. So as you already see this in Stefano's talk, and I will recall it later. So if you notice M infinity is projective over K, and you know the multiplicity freeness, you already know this. This is already know. So I think this is also explained in Benjamin's yesterday's talk a little bit. So you already know that D not tilde Robot is contained in the M squared torsion of pi Robot. Okay. So this shows 2. So you have okay. So this shows that you have this equality. So why the theorem A implies 1? So the circle, so every sigma in Serre weight appears only in the circle is m squared torsion of spiral bar. Well, because if you know, G Newton already shows that this GK dimension. Oh yeah, by G Newton shows that this have a lower bound, so it suffices to prove this upper bound, and so this is the control theorem of BHHMS. So their breakthrough is that the idea that they look at the Iwahori, they restrict to the Iwahori subgroup representation, and this already gives a lot of information. So we have they show this proposition A. So if this pi rho bar m square cubed by m square is multiplicity free, then and then they know that this, then we can show that this pi rho bar cubed by m I1 to the cube is multiplicity free. So this is a pi rho bar cubed by m square is multiplicity free, implies pi rho bar m I1 cube is multiplicity free. Okay, and remember that we if we assume theorem A, we already get 2, and by 2 we know that this is multiplicity free. So therefore we know this mi1 cube torsion of pi rho bar is multiplicity free. So here's a control theorem of Bohoi-Erstig, Hu, Mora, Shan. So if pi is a smooth admissible representation of Iwahori subgroup modular the Z1, and if this pi m I1 cube torsion is multiplicity free, then they know this GK dimensions. They have upper bound for the right upper bound for the GK dimension. Okay. So wow, this implies 1. Okay. So because by theorem A, we already know 2, so we know this multiplicity. We know this mk1 squared torsion is multiplicity free, and by the proposition A, you know this mi1 cube torsion is multiplicity free, and you just use their control theorem. Okay, this shows the GK dimension of pi is f. So this control theorem is not it's not hard to prove actually, but it's a really a genius argument. I mean, it's a very sharp observation, I think so. Let me say a word on the proof of the control theorem. So if you remember the proposition 6 of Professor Bohoi's talk in this conference, so in his proposition 6, he says that the condition m as pi fixed cubed by this m I1 cube is multi-free. So this condition implies that this is pi dual as the gradient modular pi dual here is finite generally modular over this polynomial commutative polynomial ring. So therefore, I mean, this is a polynomial in 2f polynomial ring in 2f variables modulo f relation. So the dimension here should be f. And therefore, because this is a modular over this dimension f ring, it's finite general modular over this dimension f ring, so it has most dimension f. Okay, so this is the control theorem. Okay, so let me explain the proof of A, because everything was reduced to theorem A. So theorem A is that let me remind you this. So for every sigma in the Serre weight, sigma only appears in the only appears in the circle. So namely, I mean for the m squared torsion part, so sigma only appears in the circle. So this is equivalent to theorem B. Okay. All right. Okay, so this is theorem A is equal to theorem B. It says that if for any sigma in the Serre weight, the dimension of the home of projective envelope of gamma delta representation of sigma, the module of sigma to pi rho bar is 1. Okay. Rho bar, under our assumption, rho bar is reducible. We can show that this theorem B for any sigma in the Serre weight. So this is actually equivalent to if you can find one sigma in the Serre weight, such that this home space has dimension 1, then for every sigma in the Serre weight, this home space of dimension 1. Okay, so we reduce this for any sigma to the existence of one sigma satisfy this multiplicity 1 or this dimension 1 property. Okay, so for to prove this, for you, I mean, there is a strategy to prove this. The dimension of the home space is 1. So this is first introduced by Emerton G. Savitt. So this, there is such a strategy to prove this. So namely, you should look at the patch module. So you should upgrade this to a some argument of the patch modular. So let me remind you this. So this M infinity is the patch modular, patch modular constructed by Cariani, Emerton G, Garrity, Pascunas, Shin. Okay. So this R infinity. So so this R infinity is a patched deformation ring. So it's a power theory ring over a tensor product of local deformation rings. Under our assumptions on this R bar, so all this assumption we have made on R bar, it just says that this R infinity is actually a power theory ring, okay, over this weight ring, weight vectors of F. So I'll write this M infinity for the maximum ideal of R infinity, and this is Gordic M. Okay, so this big M infinity is a patch modulo, so it's a finite generated R infinity modulo with action. Oh, sorry, it's finite generated over this R infinity with this GO2 FV action. Okay. And when you shoot to K, this M infinity is projective. And for our results, we use this minimal version of M infinity, which is in the paper of Dotto Lay. So the relation of M infinity and pi rho bar is given by this. So you take the dual of this pi rho bar is just M infinity. This patched modulo, modulo this maximum ideal of this R infinity. It's a local deformation. This is a patched deformation ring. Okay, so by the projectivity of this M infinity as a K representation, so this M infinity defines the exact functor on K representations. So you just take this as the definition of this functor, and just by the relation of M pi rho bar with this M infinity by the last one here. So you always have this. Okay. So remember that we want to show that the right-hand side, so this home K from the push of gamma tilde sigma to pi rho bar has dimension 1. So because of this relation, it suffices to show that this M infinity act on this functor, take values in this push of gamma tilde sigma is a cyclic R infinity modular. And the point is that we are reduced to do this for only one Serre weight. So this is a theorem D. Okay. So to show that this guy has dimension 1 is the same as is equivalent to show that this M infinity on this Porsche gamma tilde sigma is a cyclic R infinity modular for one Serre weight. Okay, so actually this is theorem D is what we want to check. So we check the theorem D for this only one, for this Serre weight. So this is the ordinary Serre weight. So remember that the this rho bar restricted to the inertia is some omega to the some power, right? So this Ri just appeared in that power. So we take sigma not sorry, this is practice actually should be the tensor product of a sim R0 tensor with a sim R1 and twisted by Frobenius and etc. Okay. So we take this Serre weight, and the first proposition is that if you want to check this cyclicity for M infinity on Porsche gamma tilde sigma 0, actually it can it's equivalent to check this for a quotient of this projective envelope. Okay, so there is a quotient we call it V of this projective envelope, such that this M infinity on projective envelope is R infinity cyclic, if and only if this M infinity on V is R infinity cyclic. Okay. And we can write down this V very explicitly. And because we know this V, explicit formula for this V, and we can show that this M infinity V fits into such a short exact sequence. Okay, so this is M infinity V is the kernel of this map. So from M infinity to V odd plus this direct sum with M infinity of the projective envelope of gamma now. Okay, so now here is the gamma of sigma naught, and you have this map to M infinity of sigma naught. Okay. So here this V odd is some representation which captures the Hamilton's ordinary part found. So we have this short exact sequence. Okay. So then we let me see. So we want to show that M infinity V actually is a cyclic R infinity modular. Okay. So on the next slides, I will show that this M infinity V odd and M infinity Porsche gamma sigma naught and the M infinity sigma naught, they are all cyclic modulars by the previous results we have. Well, I mean, all these known results imply this. So I will take the R infinity bar for the special fiber of R infinity. So the weight part of Serre conjecture, and so that's G with Hamilton G Savit. So this actually shows that M infinity sigma naught is a cyclic R infinity bar modular. Okay. Because the sigma naught appears with multiplicity 1 in pi rho bar as a circle. Okay. So I will write this I sigma naught for the annihilator of this modular M infinity sigma naught. So we know, so this is just the ideal is a reduction mod P of the ideal of given the crystalline deformation ring. The idea of R infinity. Remember, R infinity is a product of local deformation ring. So this I sigma naught is a ideal which gives at place V gives a crystalline deformation ring, the special fiber of this crystalline deformation ring at V associated to this sigma naught. Okay, so this is a this is a right term. This is the last third term here. And the result of Yongquan in the case of indefinite quaternion algebra, and Bordeaux in the case of definite quaternion algebra. We know that this M infinity V odd is a cyclic R infinity bar modular. Okay. And if we write this I odd for the annihilator, and actually the results also show that this I odd contains the ideal, which gives a reducible deformations of rho bar at V. Okay. And this is so the Yongquan's result and the Bordeaux gives the cyclicity of this part, and the M infinity of Porsche gamma of sigma naught, the cyclicity of this one is given by the result of Daniel Ley. So Daniel shows that this guy is a cyclic R infinity bar modular. And if we take this, I write this because it's tame deformation, so I just write I tame sigma naught for the annihilator of this modular, and so this ideal is a reduction mod P of the ideal of R infinity, which at V gives the multi-tame type deformations of rho bar. Okay. So to summarize, we know that every factor here, so these three factors are cyclic, and we know the ideals, the annihilator of this all the cyclic modulars, and the annihilators are given denoted by I sigma naught, I odd, and I tame sigma naught. Okay, so so therefore we have this exact sequence. I just replace every term by the here. So M infinity V is a is the kernel of this map. Okay. So if you look at the lemma here, so this theorem D follows from this lemma. If R is a local Theorem ring, if you have two ideals, I1, I2, three ideals, and they have this equation relation of this sub-ideals of this maximal ideal, then the kernel here is a cyclic if and only if you can check this relation. So it's I naught equals to I1 plus I2. Okay. So while we check this relation directly, and so if you so we check this relation. In fact, we check the relation as I reducible. So this ideal, we check this I reducible plus I tame sigma naught is I sigma naught. So well, so this implies that this I odd plus I tame sigma naught equals to I sigma naught. Okay. So because I mean this relation is easy to check because by the results of Daniel Ley, we already know this deformation, how this deformation ring looks like. If we check this and we use this lemma, this shows that this kernel of this map is a cyclic. So this finishes the proof of theorem D. Okay. So and the theorem D is equivalent to theorem C, which is equivalent to theorem B, and also equivalent to theorem A. So this finishes the proof of the main theorem we have. So there are some consequences also mentioned in the Stefanos lecture. Because this R infinity is a Poisson ring, we know that this GK dimension is F is equivalent to the some flatness properties as M is equivalent to the M infinity is flat over R infinity. This is already in the paper of G and Newton. And with this flatness, you can show that the specialization map. So if you this M infinity is partial modular specialized to a point is a non-zero admissible unitary binary space representation of GL to FV of GL to FV. Okay. I think this is the same in the Stefanos lecture. Okay, and this is the last slides I have, so I think I'll stop here. Thank you.
Okay, so we thank the speaker for a very nice talk.